In this fluid mechanics lecture, an introduction to macroscopic balances will be presented. These are also known as integral conservation equations for mass and momentum. We will then discuss a detailed example involving the conservation of mass for the falling cylinder viscometer. First, we consider integral conservation of mass. So we look at an arbitrarily shaped control volume, denoted here by V of t. The surface of the control volume is S of t. The unit normal vector that points outward from the control volume is n, and the local velocity of the control surface S is V sub s, which is a function of position and time. The local fluid velocity is u, which also depends on position and time. So in this case, the fluid of interest is confined within this control volume V of t. The control volume is completely arbitrary. It can translate, rotate, deform, etc. So to begin with conservation of mass, we first look at the time derivative of the total mass of fluid in the control volume. In other words, we have d by dt of the volume integral over the volume V of t of the fluid density rho dV. And we know, using the generalized Reynolds transport theorem introduced earlier in the course, also known as the Leibniz rule for differentiating integrals, that we can bring this time derivative inside the integral if we add an additional component to take into account the time dependence of the volume of integration, V of t. So what we get is, first, the volume integral of the partial time derivative of the density, and we add the additional component due to surface motion, which is the surface integral over S of t of n dotted with Vs, the surface velocity, rho ds. So that's simply an application of the generalized Reynolds transport theorem, also, as we said, known as the Leibniz rule. So next, we can substitute for d rho dt, the partial time derivative, using the continuity equation. This is simply minus the divergence of rho u. So rewriting this expression, we have that the time derivative of the total mass of fluid in the control volume is now equal to minus the volume integral of the divergence of rho u, we made that substitution from the continuity equation, plus the term due to the surface motion, n dot Vs rho ds. Now we can take this integral, the volume integral of the divergence of rho u, and apply the divergence theorem to convert it to a surface integral. So in that case, this will be the surface integral over the surface area S of t. We change the gradient operator to the normal vector n, and we have n dot rho u ds. And there's a minus sign out in front from the minus sign out here. So we can then just combine these two terms here into one surface integral to get a more compact final form. We can bring the density out in front since n dot rho u, n is operating on n dot u, the scalar rho doesn't matter, so we can put it anywhere here. Put it rho n dotted with u minus vs ds. And that's the final form of the integral conservation equation for mass. We can write it a little bit more neatly here in the next slide, and we have the exact same expression. So the left-hand side is the rate of increase of mass in the control volume, v of t, and the right-hand side is the net rate of mass flow into the control volume, v of t, across the moving control surface, s of t. We see that the normal vector n points outward from the control volume, so minus n points inward, and so minus n dotted with u minus vs is the normal component of the relative fluid velocity, that's the fluid velocity relative to the velocity of the control surface, moving into the system, into the control volume v of t. So we add that times rho, and this is basically the mass flux into the control volume. Integrate that over the surface, and that's the net rate that mass flows into the control volume. So with conservation of mass known, this is an equation you should be familiar with. You should know where to find it quickly in reference material, since we'll use this quite a bit throughout the rest of the course to solve problems and on exam 2. So with conservation of mass done, we now move on to conservation of momentum for the same arbitrarily shaped, translating, rotating, potentially deforming control volume, v of t, bounded by the surface s of t. And then we can proceed the analogous way. We start with the rate of change of the total amount of momentum of the fluid in the control volume. And this is going to be the time derivative of the volume integral over v of t of the momentum density, that's rho times u dv, and then we can apply the generalized Reynolds transport theorem, or the Leibniz rule, just like we did for conservation of mass, and we can bring this time derivative inside the integral. So we get the integral over v of t of the partial derivative of rho u dv plus a term that accounts for the variation of the domain of integration v of t with time. And so this part will be the surface integral over the surface area s of t, n dotted with vs multiplied now by the momentum density rho u ds. That's simply an application of the generalized Reynolds transport theorem for a non-material control volume that has surface velocity vs. That's where the surface term comes in here, and the Reynolds transport theorem is also known as the Leibniz rule, as we said. Now, from the equation of motion, which we derived earlier in the course, we know that the time derivative of rho u is equal to minus the divergence of rho u minus the gradient in the pressure plus the divergence of the viscous stress tensor tau plus the gravity term rho g. Consequently, we can take this first term on the right-hand side, where we have the volume integral of the partial time derivative of rho u. And this will now be equal to the volume integral of the sum of the terms on the right-hand side of the equation of motion. So we get minus the volume integral of the divergence of rho u dv. We get minus the volume integral of the pressure gradient. We add in the volume integral of the divergence of the viscous stress tensor tau. And then finally, we have the volume integral of the gravity term, rho g. That's the gravitational force per volume integrated over the volume of the system. So now what we can do is apply the divergence theorem to the first three integrals on the right-hand side of this equation. So if we do that, this first term becomes minus the surface integral of n dot rho u dv. We simply change the gradient operator to the normal vector n. This next term becomes minus the surface integral of, well, del p becomes n times p ds. And this first integral here should actually be a surface integral instead of a volume integral with the dv that we had written. And finally, this term here becomes the surface integral over s of t of n dotted with tau ds. And then we can leave the gravity term as written. So now if we put everything back together, we see that the time derivative of the total momentum in the control volume, this top term on the left-hand side, is equal to now the sum of three surface integrals corresponding to the momentum flux into the system, the pressure force on the surface of the control volume, the viscous stresses on the surface of the control volume, plus the effects of gravity on the fluid in the control volume. And we also have this final term which accounts for the influence of surface motion. So we can combine these all together. This term here, let's make this a little more clear. So this term here and this term here can be combined and written as minus the surface integral of n dotted with, in this case, u we have as the first vector, u. This one is n dot vs. There's a plus sign, minus sign in front of here, so we need another minus sign to make it plus u minus vs. Then the remaining terms here are the same, rho u. So we've combined those two terms circled in red into this integral listed here in red. And so now we have that the time derivative of the total momentum in the control volume, this top integral expression up here, is equal to the sum of four integrals. 3 over the surface area. This first term represents the net rate of momentum flow into the control volume by fluid flow relative to the motion of the control surface. Next term is the pressure force, which acts to increase the momentum of the control volume, minus n points out, so minus n points in. Therefore, this is the force of the fluid surrounding the control volume on the fluid within the control volume. And finally, these are the viscous stresses exerted by the fluid outside the control volume on the fluid inside the control volume. And then we have the effect of gravity on the fluid within the control volume. So we can combine all of these terms together, group them as we showed, And we get this general statement of conservation of momentum. So this integral on the left-hand side, as we just said, is the rate of increase of the momentum in the control volume, v of t, and that's equal to the net rate at which momentum is convected across the control surface, s of t by fluid flow. That's this term here. So once again, minus n points into the control volume, minus n dotted with u minus vs gives the normal component of the fluid velocity relative to the control surface into the control volume. So this is the fluid velocity flowing into the control volume multiplied by momentum density. So the product of these two terms is the momentum flux going into the control volume with the minus sign included. We integrate the momentum flux over the control surface. We get the total rate at which momentum goes into the control volume due to fluid flow across the control volume, also accounting for the motion of the control surface. And then finally, the last three terms are the sum of the forces acting on the fluid in the control volume. We have the effect of gravity, body force, gravity density integrated over the control volume gives you the total gravitational force on the fluid within v of t. This next term is the total stresses exerted by the fluid outside the control volume on the fluid inside the control volume. N points outward, so it's the force or the stress exerted by the fluid towards which n points, the stress outside, tau minus pi. This is equal to the viscous stress tensor sigma. We broke them up into two components for the fluid. And we've also broken up this integral into another part. If there's any solid bounding the fluid, we write n dot sigma for the solid. So this would be the force the solid exerts on the fluid. We don't really know what sigma is in a solid, and so we typically rewrite this term as shown. So the integral of the stress over the solids, any solid surface bounding the fluid in the control volume, we designate as FSF, the force the solid exerts on the fluid. And this is the negative, based on Newton's third law, of the force the fluid exerts on the solid, FS, as we've used in previous lectures. So, as we said, the surface force terms have been split into two parts. One integral over the fluid, the second integral over the solid, that we denote FSF because we don't really know much about the stress tensor in the solid. The contribution of the viscous stresses, this n dot tau in this integral here over the fluid, is often neglected relative to the force and the pressure. It's for two reasons. One, it's typically smaller than the pressure force, and two, in order to compute this, we need to know details of the fluid velocity profile. These are usually complex flows in complicated systems, and as a result, we don't typically know the details of the velocity profile, and as a result, we don't know the viscous stress tensor, and so we can't really compute the viscous stresses exerted on the control surface. And as I said, they're almost always small relative to the pressure stresses and pressure force anyway. And so, as a result, we usually neglect that term there. And then finally, as we've already kind of mentioned, the force exerted by, if this is positive, or if this is negative on a solid surface, is often unknown, and it's determined from the integral momentum balance. So typically, we apply this integral momentum balance to determine the force the solid exerts on the fluid or that the fluid exerts on the solid. So we're trying to determine this force FSF. And so we usually can figure out each of the other terms, especially at steady state when the time derivative term vanishes. These other terms are usually straightforward to compute. And so we can then use the integral momentum equation, this macroscopic momentum balance, to solve for the interaction force between the fluid and the solid, which we designate as FSF, which corresponds to this integral shown here. So that's typically the utility of this equation. So, with the integral conservation equations for mass and momentum now derived, we can move on to an example of how to apply the integral mass balance for a semi-complicated system. So the example we look at is mass conservation for what's known as a falling cylinder viscometer. So this is the schematic diagram shown here, and as we say in the problem statement, the viscosity of a liquid can be determined from the speed u at which a solid cylinder of radius r2 falls through a closely fitting tube of radius r1 filled with liquid. So as shown here, we have a cylindrical tube, that's this outer thing, with a bottom. It's filled with liquid. And we place a closely fitting cylinder within the tube. Now this cylinder is more dense than the liquid, so it falls downward at velocity u under the influence of gravity. And then there are forces exerted on this cylinder, so eventually we essentially reach a steady state when it's far enough away from the bottom of the tube. So the gravitational force down is balanced by the shear stress integrated over the sides of the cylinder, plus the difference in pressure exerted on the bottom and top faces of this moving cylinder. So the cylinder we have that moves downward has radius r2. The tube itself has radius r1, which is obviously larger than r2. Cylinder has length L. It's some distance, let's say h, above the bottom, moves downward at velocity u. We're assuming it's constant velocity for the time period of consideration. We have the coordinate system shown here, z directed upward, r directed radially outward from the center line. And this is filled with liquid. Above the liquid is air, and then gravity acts downward. So the first thing we say is, what's a qualitative statement of conservation of mass? In other words, an overall macroscopic mass or material balance for this system. So I'll give you a few moments to think about that. You can pause this video if you like, and then we'll discuss the answer. So in this system, overall macroscopic mass balance says the rate at which the liquid is displaced by this falling cylinder must equal the rate at which the liquid flows upward through the gap, this annular gap between the cylinder and the tube. So we would displace liquid at a rate of pi r2 squared, which is a surface area at the bottom multiplied by u. So pi r2 squared u is the rate at which this moves downward, and that then has to be equal to the integral of the z component of the fluid velocity over this annular gap done in cylindrical coordinates. So basically, this cylinder pushes fluid downward, it displaces fluid as it moves down. Because this liquid is confined by the walls on the side and the bottom, it has nowhere else to go but up through the gap between the inner cylinder and the cylindrical tube. So that's a qualitative statement of conservation of mass. That's something you should all be able to do without too much thought at this point in the course. Next, we want to make this more quantitative and use a macroscopic mass balance to relate the fluid velocity in the annular gap to these parameters, u, r1, r2, and anything else that might appear. And we see now we've designated the height of this cylinder above the bottom as h of t. So we can kind of do this by inspection based on the qualitative statement we just gave, but I want to illustrate how one would apply the integral statement of mass conservation in detail to the system. And there's two choices of control volumes that one might identify upon brief inspection, and so we'll discuss how to proceed using either of those. So the first case, let's use this shaded yellow region as the control volume. So it encompasses all the fluid that lies below the falling cylinder and also extends some distance upward into the gap. So if we look at this control volume from above, it looks something like this, two concentric cylinders. This inner region, S2, corresponds to the cylinder that's moving in this case here. And there's no fluid flow relative to that, so we don't have to really consider this too much. And then this outer region, S1, this annular region, that's the annular gap between the tube and the cylinder. So surface area S2 is pi r2 squared. The area of this annular gap S1 is the difference between the area of the outer circle and the inner circle. So it's pi r1 squared minus r2 squared. So next, we want to identify various parameters so we can apply the macroscopic mass balance. So we'll write out the mass balance here, just so we recall what it is. So we have the time derivative of total mass in the volume, and that's equal to minus the surface integral of rho times the normal component of the relative velocity, u minus vs ds. So we want to apply this case in the system. And so our control surface will encompass the top here. The top has two parts, S1, the gap, and S2. S2 corresponds to, let's say, the bottom of this cylinder. And then the control surface also includes the side of the cylinder, the side of the container, and the bottom of the container. However, we don't really have to consider the sides of the container or the bottom in much detail because they're impermeable solid surfaces, no flow across them, and they're also not moving, so they're not really much of interest. What really matters is going to be this top surface comprised of S1, the angular gap, and S2, the bottom, let's say, of this cylinder. So on this top surface, we can identify the normal vector n as the unit vector in the z direction, Ez. Because z points up, we want the normal vector pointing out of the control volume, and so it'll be Ez on top pointing out. Now, we can say that on S1, well, surface S1 is this outer angular gap, so that's not moving. So what we have is Vs equals 0 on surface S1, because in this region right here and this region right here, the control surface is fixed. Even though the cylinder is moving down, our control volume is not moving in that particular location. So surface velocity is equal to 0. And what is u? Well, u is simply the fluid velocity in the gap. Then we can look at S2, which would be the bottom of the cylinder. So we come here, and this is going to be S2 down here. So S2 is moving at velocity Vs is equal to minus u Ez. Why is it minus? Well, the cylinder is moving downward at velocity u, z points upward, and so it's moving in the minus z direction. So Vs is equal to minus u Ez. What's the fluid velocity at the interface with the bottom of the cylinder surface? Well, u is equal to Vs from the no penetration boundary condition. So we see that u minus Vs will actually be equal to 0 on surface S2. The other thing we can do is say, now what is the volume V of t as defined here? So the volume is going to be the part on each side. So if we continue this down here and then down here, we have this region and this region. We have basically the angular gap, but extended all the way down. And so we can call this distance here from the bottom to up there h1. h1 is going to be a constant because that part of the control volume is not moving. And so our volume V of t is equal to pi times r1 squared minus r2 squared. That's the area of the angular gap. Now we multiply by the height of that region, which is going to be h1. So that accounts for the part that's cross-hatched. And now we have to account for the volume below the cylinder. The volume below the cylinder is going to be plus the surface area of the bottom of the cylinder, pi r2 squared, multiplied by this distance, which we have listed as h of t. So now we can apply that to this equation here. The density is constant, so the integral of the density over the volume is simply the product of the density and the volume. So this time derivative term in our macroscopic mass balance becomes the time derivative of the product of the density and the volume. So we get pi r1 squared minus r2 squared h1 rho plus pi r2 squared h of t rho. And then now this is equal to the integral of rho n dot u minus vs over the surface area S. And we'll break this up into two different integrals. So we get minus the integral over surface area S1, the angular gap, of rho n dot u minus vs ds. And then we add in the other contribution over the surface area S2 of rho n dot u minus vs ds. And we've already said that on S2, u is equal to vs due to the no penetration boundary condition. So u minus vs is equal to 0, and this entire second integral vanishes. For surface area S1, the top surface here is not moving, and as we said, vs is equal to 0. So that's equal to 0. And what we get instead is simply, well, we can go a step further. We can say, well, what is n on that surface? We already said that n is equal to Ez. So we get Ez dot u, which is just the z component of u, or uz. And so the surface integral terms simplify to minus the integral over S1 of rho uz ds. Then we go back to this first term, and we see we're taking the time derivative of two terms, the time derivative of pi r1 squared minus r2 squared h1 rho. This entire term is constant. So nothing changes. In the second term, h of t depends on time, and so there's going to be a non-zero contribution from that. So if we go back to this integral over surface area S1, we now want to write this out using cylindrical coordinates. So this is minus, let's bring the density outside since density is constant. We integrate from 0 to 2 pi, and we integrate over the angular gap. With respect to r, we integrate uz, and then the integration area element is r dr d theta. Don't forget the r term here. And we're integrating from the inner surface to the outer surface. The inner surface is r2. The outer surface is r1. And so this is equal to, we can do the integral over theta, since there's no theta dependence on this thing due to symmetry. So we get minus 2 pi rho times integral from r2 to r1 of uz r dr. And this is then equal to what remains from the first term. We said the constant term, well, it's time derivative 0. So what's left here is pi r2 squared rho d h dt. Now we can say, what is dh dt? What's the rate at which h changes in time? Well, it's equal to minus the velocity of the cylinder. Because the cylinder is moving downward, it's decreasing h of t, so dh dt is negative, and it is in fact equal to minus u. So now we have a minus sign here. That cancels the minus sign here. We can cancel pi and pi. We can cancel rho and rho. And so what we're left with in this expression here is, and we'll write this in, let's say, blue to make it stand out a little bit. We have the integral from R2 to R1 of uz r dr is equal to R2 squared u divided by 2, where the 2 comes from this term here that was left over. And so that's the final simplified form of conservation of mass for this system. You can actually highlight it a bit. That's the final result. So that's the net result of conservation of mass applied to this particular control volume. We went through this probably in more detail than you would actually have to. Like I said previously, you could take the qualitative statement of conservation of mass and just substitute in the mathematical expressions for the integrals and arrive at this as well. But it's good practice a few times to actually go through and simplify the terms in the integral mass and momentum balances. We'll do it here for mass. We'll do one more example, the same example with a different control volume, and we'll go over an example in one of the next lectures using the detailed conservation of momentum and simplifying the various terms. Then we'll show simplified versions of the macroscopic mass and momentum balances that can be used in, let's say, 95% of the types of problems that we would consider. And they are much simpler and much quicker to apply, and therefore much more convenient. But before we get to them, it is good practice a couple of times to go through simplifying the terms in the detailed integral expressions, just to gain confidence and to gain practice understanding how to actually simplify these terms. Because occasionally one deals with complicated systems in which you have to actually revert to these forms instead of the simplified forms, and understanding how to simplify the various integral terms is important. Okay, the second case now, we'll use a different control volume. So the control volume we used so far extended some distance up above the annular gap between the cylinder and the tube. In this case, let's use this control volume here, which is simply the area, well, it's the volume below the cylinder. It doesn't extend up into the annular gap at all. And so as this cylinder moves downward at velocity u, the entire top surface of the control volume is going to move downward at velocity u as well. And that's going to be the primary difference between this case and the one considered previously. So this surface, let's make that a little better. This surface here is going to move downward, and this surface here is going to move downward at velocity u along with the cylinder. So the question is, how do we apply the mass balance to this particular system? Well, we look at it, and the first thing we can say is we still have these two surfaces, S1 and S2, but they're both moving downward at velocity u. So, first of all, the volume V of t is going to be equal to pi r1 squared times h of t, because the entire top surface, S1 and F2 combined, the entire top surface moves downward at velocity u, and therefore this is the volume. It's the entire top surface area, which is the outer part of S1, pi r1 squared, multiplied by the height h of t. And then now we can look at the two parts of this composite surface. On S2, as we had before, Well, the surface velocity is equal to minus u ez, and the fluid velocity is equal to the solid velocity due to the no penetration boundary condition. Now on S1, Vs is also equal to minus u ez, because the entire top surface of our control volume is moving downward at the same velocity. However, the fluid velocity u is not equal to the velocity of the control surface, because the fluid is flowing up through the gap. It's being displaced by the downward moving cylinder, and so the fluid moves up, the control surface moves down, and so u minus Vs is not equal to 0 on S1. It is, however, equal to 0 on S2 due to the no penetration boundary condition, because S2 corresponds to a solid surface. All right, so now we can apply the macroscopic mass balance. We have the rate of change of the total mass in the volume, and since the density is constant, it's just the product of the density and the volume V listed here. So we get rho pi r1 squared h of t, and this is equal to, we can write the surface integral, break it up into two parts over surfaces S1 and S2. On S1, we have rho n dot u minus Vs ds, and we write out the term for S2 as well, just for completeness, over S2, rho n dotted with u minus Vs ds. Now, as we've said, u minus Vs on S2 is equal to 0 because of the no penetration boundary condition, and so the entire integral over S2 vanishes. On S1, we know simply that n is equal to the unit vector in the z direction. And so now we can simplify this a little bit. This term here, everything's constant but h, so we get rho pi r1 squared dh dt is equal to minus rho times the surface integral ez dot u gives us uz, ez dot minus Vs. Well, Vs is minus u ez, so minus Vs is plus capital U ez. Ez dotted with plus capital U ez gives us plus capital U ds. And then we can write out this integral in cylindrical coordinates, so we get minus rho times the integral from 0 to 2 pi times the integral now over the annular gap, which we go from R2 at the inner surface to R1 at the outer surface, of uz plus capital U r dr d theta. And if we write this out, we can do the theta integral since there's symmetry and there's no theta dependence. So we get a minus rho times 2 pi, and then we're left with the integral from R2 to R1 of uz plus capital U r dr. So the first term, we simply get the integral from R2 to R1 of uz r dr. And then the second term, we get plus capital U times integral from R2 to R1 of R dr. Now, this second integral is simply 1/2 little r squared evaluated from R2 to R1. So in other words, it's equal to capital R1 squared minus capital R2 squared divided by 2. And then it's multiplied by minus rho times 2 pi out in front. So what we can do here is we can cancel this row with this row. We can cancel this pi with this pi. And so what we're going to get from the left-hand side, well, the final thing we can note on the left-hand side is that, just like before, dh dt is equal to minus u. And it's minus because h is decreasing in time as the cylinder falls down, the height gets smaller, and u is in the downward direction, the minus z direction, so it's minus u. And so we can also cancel the minus signs if we like. We can make this a plus and make this a plus as well. And so now what we're left with on the left-hand side is R1 squared u is equal to, now we have 2 times the integral from R2 to R1 of uz r dr. And then the second term, we get plus, the 2 out in front cancels the 2 down below, so we get plus R1 squared minus R2 squared multiplied by capital U. And so what we see immediately is the R1 squared U on the left-hand side cancels with the R1 squared U on the right-hand side, and therefore, if we put everything together and just bring this minus R2 squared U to the left-hand side and divide by 2, we find the same result as using the previous control volume, namely the integral from R2 to R1 of uz r dr is equal to 1/2 R2 squared multiplied by capital U. The same result we found using the other control volume. And that, of course, should happen. If we have the right answer, it should be independent of the particular choice of control volume that we make. So this gives us the exact same result as before, confirms that it works. And so it's good to practice to use different control volumes and be able to get the same result using each, and namely get the correct result using each. So these are good examples to go through and practice with. And then if you like, you can look at the simplified macroscopic balances that are given on Moodle in a handout, and you can try to apply those to each of these two systems as well and make sure that you can recover these same results. You can also just go from the qualitative statement we made at the beginning and then just convert that to a quantitative statement, avoiding all these intermediate steps we made, just writing it directly, and see if you're comfortable doing that as well. All right, so that concludes the examples of the macroscopic mass balance, or applying the integral conservation of mass. We'll go over an example with integral conservation of momentum as well in the next lecture. But for now, there's one additional equation that's often helpful in systems where we apply these macroscopic mass and momentum balances. And it's known as Bernoulli's equation. This is actually a simplified form, basically used for inviscid fluids, fluids where the viscosity is essentially negligible, so high Reynolds numbers, we can neglect viscous effects. It's a simplified version of what's known as the engineering Bernoulli equation that we'll talk about in a couple of lectures. But some of the terms in that equation are too complicated to evaluate for certain systems, especially systems where there's high Reynolds number and viscous effects are safely neglected relative to pressure and inertia. And so Bernoulli's equation is a very simple and very useful tool in those cases. So how do we get to Bernoulli's equation, and what exactly is it? Well, we start with the Cauchy momentum equation. So conservation of momentum for a fluid. Doesn't have to be Newtonian, it can be arbitrary right now since we're neglecting the viscous stresses. Doesn't really matter what the rheological properties are. So what we have is that rho du dt plus u dotted with del u, inertial terms, are equal to minus the pressure gradient term plus rho g plus del dot tau, the viscous stresses. And what we're going to do is neglect the viscous term for what we call an inviscid fluid. Inviscid fluid is also sometimes called a perfect fluid or an ideal fluid. Those are sort of historical names, but if you see that in a problem statement, it's hinting that you want to use the Bernoulli equation. It's inviscid, ideal, or perfect. This corresponds to a frictionless fluid. In other words, one in which there's no viscosity. The viscosity goes to 0. So the remaining part of the momentum equation is known as the Euler equation. That's conservation of momentum for inviscid fluid. The next thing I want to do is just remind you of a vector identity. So u dotted with del u can be written as the gradient of 1/2 scalar u squared minus u cross del cross u. Now here, scalar u is equal to the magnitude of the vector u, the velocity. So this is simply a vector identity. And one can prove this rather straightforwardly using index notation that we introduced earlier in the course. Now, if the flow is irrotational, omega, which is equal to the curl of the velocity, vorticity is equal to 0, and the velocity can be written as the gradient of the velocity potential phi. Both of which we discussed earlier in the course. So now we can just rearrange the Euler equation. We can substitute the velocity potential for the velocity in the first term. So what we get is rho multiplied by the time derivative of the gradient of the velocity potential, plus, now we're going to use this vector identity for u dot del u, so we have plus rho times the gradient of 1/2 u squared, and then we have the second term, but del cross u is the vorticity. We just said that's equal to 0 for irrotational flow, so we can neglect that term. And then we have the right-hand side, so we have minus the gradient in the pressure, plus we can write the rho g term as the gradient of rho g dotted with x, where x is the position vector. So now we can divide by the density, assuming it's constant density in this case. And then we can bring everything to one side and put it within the gradient operator. So what we get is the gradient. Let's make a nicer gradient. So the gradient of the time derivative of the velocity potential. We simply interchange the order of the derivatives, the time derivative and the gradient operator, which we can do if these are continuous functions in space and time. So we have that first term. The second term now becomes 1/2 magnitude of velocity squared. This term, if we bring it to this left-hand side, we get plus pressure divided by density. It's important not to confuse the two, even though they look sort of similar when I write them. Make sure you understand the difference between pressure and density. And then we have minus g dot x, which accounts for the effects of gravity. And the whole thing is equal to 0 if the vorticity is equal to 0. In other words, if it's an irrotational flow. Now, in most cases, it's more convenient to write minus g dot x is plus g times h, where h is equal to the height above some reference plane, in the direction opposite to gravity, of course. So you simply pick some convenient location to set h equal to 0, or to use as the origin of the z-coordinate in your problem, and then h would just be the distance above it if it's positive, distance below it if h is negative. And the choice of the reference plane is completely arbitrary. It's just made as a matter of convenience for the particular problem. So what we found here is a form of the Bernoulli equation for irrotational flow. Namely, the gradient of this quantity in parentheses is equal to 0, if the flow is irrotational. If the gradient is equal to 0, it's saying this quantity in parentheses doesn't change. In other words, this quantity in parentheses is a constant everywhere in an irrotational flow. That's a very convenient result that we'll get back to in a moment. The second thing we can do is derive a version of Bernoulli's equation for a steady rotational flow. So we go back to the Euler equation that we had before with the simplifications we made. So we write it at steady state as the gradient of 1/2 velocity magnitude squared, 1/2 u squared. And we have minus u cross del cross u. Del cross u is still the vorticity, but in a rotational flow, the vorticity is not 0, so this term is not equal to 0. And this is equal to now the gradient of the pressure divided by the density plus g times h, using the terminology we introduced on the previous page. Using gh, h is the height above some reference plane, once again in the direction opposite to gravity. So that's the Euler equation. With the gravity term simply written as a potential using h, the height above the reference plane. So now what we want to do is take the dot product of the velocity with the Euler equation. So what we get is u dotted with the gradient of 1/2 u squared minus u dotted with this term here, the u cross del cross u, and that's equal to this has a minus sign in front, of course, and that's equal to minus u dotted with the gradient of the pressure divided by the density plus g times h. Now what can we say about this term here? Well, by the nature of the cross product between two vectors is perpendicular to each of the vectors. So u cross del cross u is going to be perpendicular to the velocity. The dot product of two perpendicular vectors is equal to 0. And consequently, this term vanishes. So what we get for a steady rotational flow is u dot the gradient of 1/2 u squared plus the pressure divided by the density plus g times h is equal to 0. So physically now, what does this correspond to? Well, if we have the gradient of something and then take the dot product with a vector, that gives us the rate of change in the direction of the vector. So this is proportional to the rate of change parallel to the velocity field. So what are curves that are everywhere parallel to the velocity field from earlier in the course? Well, they're simply streamlines. So what we found here is that for steady rotational flow, 1/2 u squared plus the pressure divided by the density plus g times h is constant along a streamline. It's not quite as powerful as a result for irrotational flow. For irrotational flow, this ends up being a constant everywhere in the flow. For rotational flow, it's constant along a streamline due to the fact that the vorticity term doesn't vanish for rotational flow. This is only 0 when it's taking the dot product with u. So this is only 0 along a streamline. So summarizing the two results in two cases, Bernoulli's equation, for steady inviscid flow, we have two choices. One, we say that 1/2 u squared plus p over rho plus gh is equal to constant along a streamline. So in this case, in rotational flow, if you wanted to apply Bernoulli's equation, you would take 2 points along the same streamline and set these two things equal. That can be useful to determine the velocity at one point if the velocity is known at another point in the flow, or it can be useful to determine the pressure at one point if the pressure and velocity are known at another point in the flow. So if you have one unknown along the velocity and pressure or elevation, saying this is constant along a streamline, you can then apply this at 2 points and determine that unknown at a second point if the values are all known at the first point. More powerfully, if the flow is irrotational, then we see that the gradient of this quantity is equal to 0 everywhere. In other words, 1/2 u squared plus p over rho plus gh is constant everywhere in the flow. And so we can apply this at any 2 points. The 2 points do not have to be along a streamline if it's irrotational flow. They can be any 2 points anywhere in the flow. And so once again, it's very useful for determining, or at least estimating, the velocity at one point if it's known somewhere else, and if you know the pressures and elevation change, or if you want to figure out the pressure at one point if you know the velocities at 2 points, elevation at 2 points, and you know the pressure at another point. So Bernoulli's equation is a very useful adjunct to the macroscopic mass and momentum balances, particularly momentum. When you're applying a macroscopic momentum balance, you might have an unknown quantity, a velocity or a pressure at one surface or one location, and you can often use Bernoulli's equation to determine that unknown quantity and then be able to apply conservation of momentum. So this is often used along with conservation of momentum, rarely by itself in solving problems. And as we said earlier, a more general version of this is known as the engineering Bernoulli equation, also known as the mechanical energy equation. And that accounts for viscous effects to some extent, viscous losses in bends, fittings, due to friction factors in pipes, etc. We'll get into that in a couple of lectures. So finally, a couple of notes. If the fluid is inviscid, meaning viscosity is zero, or at least approximately zero, so inertial effects are highly dominant, an irrotational flow remains irrotational. So if it's irrotational at one instant in time, it will always be irrotational at any other instant of time. Moreover, if the flow is irrotational at one location, it is irrotational at every location, provided viscosity can be neglected. And also, the irrotational flow approximation is often accurate for engineering analysis of flow at large Reynolds numbers, even if it's not exactly irrotational, which nothing truly is. It's still very accurate within 5 or 10%, which is within the margin of error we typically have when applying these macroscopic balance equations anyway. So today we've introduced 3 very useful tools for the analysis of engineering problems: the integral mass and momentum balances and Bernoulli's equation. You can complement this with the integral angular momentum equation, which we won't have much occasion to use, and also the engineering Bernoulli equation, or the mechanical energy balance, which we'll introduce in a few more lectures. And those things together are the set of tools we have for analyzing many real-world problems that are too complex to solve exactly, either analytically, which very few things can be done, or even numerically on a computer, due to either time or computational resource limitations.